Welcome to the lecture series on Digital Electronics 18 EC302C. Today's lecture we are going to learn about demultiplexers. In particular, we are going to learn what is a 1 to 4 demultiplexer will do and how to write its truth table and how to draw it, the combinational logic circuit of the 1 to 4 demultiplexer. So before going to see exactly what is a 1 to 4 demultiplexer is, we'll see what is a demultiplexer and what is the function of a demultiplexer. So a demultiplexer is a combinational logic circuit which takes digital information from only one single line and distributes it to a given number of output lines. So this function is, you can see that it is exactly the opposite function performed by a multiplexer, where you can see that multiplexer takes the digital information from a number of lines and transmits that information to a single output line. So here the function of the demultiplexer is the opposite. So it takes digital information from one line and this demultiplexer distributes it to a given output number of output lines. So since it is distributing the data present on the single input line to a number of to a given number of output lines and to a given number of output lines, sometimes it is called also called as a data distributor. So if we see another way or more precisely from circuit point of view, a demultiplexer is the logic circuit that receives information through a single input line and transmits the same information over one of the possible 2 power n output lines. So this is 1 to 2 power n, I can say demultiplexer. 1 to 2 power n demultiplexer. The number of input lines will be only 1. The number of output lines will be 2 power n. And the whatever the data that is coming on the input line must be distributed to one of the 2 power n output lines. So how to select then one of the 2 power n output lines? And for that you require select inputs or selection inputs. So there will be n selection inputs present for 2 power n to select one out of the 2 power n output lines. So the selection of specific output line is controlled by the bit combinations of the select lines. So here we have shown the symbol given for the 1 to 4 demultiplexer. So 1 to 4 demultiplexer means it is one input line on which the digital information is taken by the demultiplexer and 4 output lines indicated with D0, D1, D2, D3, onto which the digital information will be distributed according to the selected output line The selection of one of these four output lines is done by using selection inputs S1 and S0. So this is so we'll discuss one uh, important demultiplexer circuit here, that is 1 to 4 demultiplexer. And in as we have said, 1 to 4 demultiplexer means the number of input lines are 1 and the number of output lines onto which the data is to be distributed is 4, and since 4 is equal to 2 power 2, so that means there should be two selection inputs to select one out of the 4 output lines, and let the designations of those selection inputs are S1 and S0, and say the outputs for the demultiplexer are D0, D1, D2 and D3, the 4 outputs. And what is the input? The input is the data input, say it is D. So there is only one input, and that information on the input line will get distributed over a number of output lines. So depending on what are the bit combinations of the selection inputs. So since we have two selection inputs S1 and S0, and the two inputs can take four different bit combinations 0 0, 0 1, 1 0, 1 1, and we'll see with each bit combinations one of the output line will get selected and the input digital information will be placed on that output line. So if S1 is 0 and S0 is 0, for this combination of the selection inputs, the D0 line output line will get selected, and whatever the data that is present on the input line will get transferred to the first output line D0. So now D0 equals D, where D is the data present on the input line of the demultiplexer. So when selection inputs are 0 and 0, D0 output line is selected, and the data present on this line is same as the data coming on the input line. And what about the remaining outputs? They will be 0. But the data present on the remaining outputs which are not selected on those lines, the data will be 0. And here we can show that D1, D2 and D3 are 0 since they are not selected. Similarly, when S1 equal to 0 and S0 equal to 1, the second output line D1 will get selected, and whatever the digital information that is present on the input line will be transmitted to the D1 line. So D1 equals D, and the remaining three output lines will be 0. And similarly, when S1 equal to 1 and S0 equal to 0, the third output line D2 will get selected, and the data on D2 will be same as the data present on the input line of the demultiplexer. And when the selection inputs S1 equal to 1 and S0 equal to 1, the fourth output line D3 will get selected, and whatever the information that is present on the input line will be transmitted to the D3 line, and the other output lines will have 0 since they are not selected. So this is, I can say, the truth table of the 1 to 4 demultiplexer, which is showing the selection inputs on left side and the outputs on right side of the truth table. So here for each combinations of the selection inputs, one particular output line got selected, and whatever the digital information that is present on the input line will be transmitted to the selected output line. So next we look at the combinational logic circuit of the 1 to 4 demultiplexer. So here we have shown the symbol of the 1 to 4 demultiplexer with ER. We can say, you can call it as D, data input, and this is the data line, input line, in which the data is coming, and 4 output lines D0, D1, D2, D3, and 2 selection inputs S1 and S0. So depending on the combination of bits for the selection inputs, so one of the output line selected, and the data present, the digital information present on the input line will be transmitted to selected output line. So that means, so here we have shown at the left the combinational logic circuit of the 1 to 4 demultiplexer by using basic logic gates. So here you can see that this is the data input, that is the input line, and these are the data output lines, the 4 data output lines, and here we have the selection inputs S1 and S0. And to draw this circuit, we can derive the algebraic equations for all these output lines from our the truth table that we have discussed previously here. So from this truth table we can obtain the Boolean expression for all the 4 outputs, that is D0, D1, D2 and D3 also. And once we obtain the Boolean expressions, then we can draw the logic circuit using any of the logic gates. So here the D0 equals D only when S1 is 0 and S0 is 0. So that means I can write D0 as D0 equals S1 bar S0 bar dot D. So here D0, the Boolean expression for D0 output equals, since D0 equals D only when S1 equal to 0 and S0 equal to 0, and in that case the D0 equals D. So this can be written as D0 equals S1 bar dot S0 bar dot D. D S1 bar S0 bar. And similarly, D1, for D1 I can write the Boolean expression as, so D1 equals D only when S1 is 0 and S0 is 1. So I can write D1 as S1 bar dot S0 dot D. So D1 equal to D S1 bar dot S0. Similarly, the Boolean expression for D2, you can see that D2 equals D only when S1 equals 1 and S0 equal to 0. So I can give the expression for D2 output as S1 dot S0 bar dot D. So D2 equal to D dot S1 dot S0 bar. So similarly, I can write the expression for D3 output also. D3 is equals D when S1 is equal to 1 and S0 equal to 1 only. So I can write D3 equals S1 dot S0 dot D. So D3 equals D S1 S0. So by making use of the algebraic equations or the Boolean equations for all the four outputs, I can draw the logic circuit diagram of the 1 to 4 demultiplexer. So here I can see that my some of the outputs require the selection inputs in to be present in complemented form. So since my selection inputs are available in original form, so I use two NOT gates to obtain the complemented form of the selection inputs S1 and S0. So here you can see that the S1 is applied to one NOT gate to obtain S1 bar here, S1 bar, and here S0 is also applied to one more NOT gate to obtain S0 bar here. So with this now the selection inputs are available in their original and the complement form, and now the all the four outputs can be obtained by using four AND gates with uh, three input AND gates for which the inputs are as specified in the expression. So to obtain D0 we have to use the first AND gate with the inputs D, the data input D. So this is our D data input, and for the first AND gate one of the input is D and other is S1 bar. So this is S1 bar and the second input is S0 bar. So if the inputs are connected in this way, we will be able to um, realize the Boolean expression for the D0 output. Similarly, we can realize the Boolean expression for D2 by using the second AND gate number 2, by giving the inputs as D, S1 and S0 bar. Similarly, we'll be using the third AND gate. Oh, sorry. Using the third AND gate to realize D2 expression for D2 output, and we'll be using the fourth AND gate to realize the expression for the D3 output by giving D S1 and S0 as the input. So this is D input and this is S0 and this is S1. So this is the combination logic circuit of the 1 to 4 demultiplexer, and this is how we can realize the output expressions for the 1 to 4 demultiplexer. And now we'll look at how we'll verify and see whether the selection of the particular output line is done properly or not by applying a particular set of the selection inputs. So we'll assume that the select input combination S1 S0 is 0 1. So assume that S1 equal to 0 and S0 equal to 1. S1 equal to 0 and S0 equal to 1. So we'll assume this particular combination. So by this you can see that while S0 is 1, S0 bar this equals 0, and while S1 is 0, S1 bar is 1. So the gate, the AND gate, that particular AND gate is enabled for which both the inputs are 1 1 apart from the data input. So for which AND gate is enabled, for which the input is S0, one of the input is S0 and the other input is S1 bar. So that is it AND gate 2? Yes, it is AND gate 2, for which the inputs are S0 which is equal to 1 and S1 bar which is equal to 1. So for this AND gate the two inputs are 1 and 1 and the other input is your data input. So this data input goes to all the AND gates, but the other two lines will change depending on what are the selection lines or what are the bit combinations chosen for the selection lines. So for the given for the chosen bit combination of 1 0, for the AND gate 2 the we have the two inputs as 1 and 1 apart from the data input. So the output of this data AND gate, that is D1, now equals, it is 1 dot 1 dot D, and which is equal to your D. So D1 equals D, that is the D1 outline got selected and whatever the data that is present at the input will be transmitted to the outline D1. So if you choose other different combination for the select lines, then you will be going to select the different output data output line, and the input data will be placed on that selected output line. So here you can see that considering the selection input combinations S1 S0 equal to S0 1, the AND gate is associated with the D1 will have two of its inputs equal to logic 1, and a third input is connected to D. So therefore the output of this AND gate is according to the information provided by the data input. So the remaining AND gates have logic 0 at least uh, as one of their inputs, which makes their output equal to 0. So at the same time we can see that So at the same time, you can see that for the first AND gate, um, S0 is the input, so this input is 0 and this input is 1, so the output is equal to 0. So we have to also show the remaining outputs. And for the third, so second we finished. First, third AND gate, one of the input is S0 bar, so it is 0, and the third input is S1, which is also equal to 0. So D3 is also equal to 0. Similarly, the fourth AND gate, for the fourth AND gate, one of the input is S0, which is equal to 1, and the second input is S1, so which is equal to 0. So as one of the input is 0, that D3 is also equal to 0. So except for the second AND gate, for the remaining AND gates 1, 3, 4, one of the input, at least one of the input is 0, so the outputs are 0. So you can see that there are certain number of applications for the 1 to 4 demultiplexer. The important applications are the communication systems and the telephone networks. So where you want to transmit a number of signals over a single transmission line, and you want to separate the data at the output side, that and separated output can be transmitted over a number of output lines. So then there you can use the demultiplexer at the output, and you can see that a decoder. So normally a decoder circuit with enable input functions as the demultiplexer. So demultiplexer circuits can be obtained from a decoder IC. So a decoder IC can be modified and can be used as a demultiplexer circuit. A 1 to 4 demultiplexer can also be used in applications of serial to parallel converter also. So, so if there is a single communication channel, transmission channel, and if you want to transmit, or if the data has been transmitted serially from source to the destination, then at the destination side you have to convert the data back to parallel from serial, and this serial to parallel conversion can be achieved by using 1 to 4 demultiplexer. So this is very necessary because uh, the data processed by the computer, digital computer, is parallel data, but when you want to transmit the data, if you transmit the data parallelly, you require more number of transmission lines, which is not economical, and from the economic point of view, you transmit the data serially. and at the receiving end, or when the data is to be processed by a computer, the serial data received on a single transmission line, single channel, should be converted back to parallel, and this can be achieved by using the demultiplexer. So overall, the demultiplexer is very useful application in communication systems and telephone networks and in serial to parallel conversion. So next we'll look at some of the important IC numbers from both TTL and CMOS family of the demultiplexer ICs. So here we have already stated that a decoder with enable input can be used as a demultiplexer. So we have ICs which can function both as decoder and demultiplexer depending on the connections. So here we have given the popular IC numbers from both the families. So here the first one is 74155. It's a dual 2-line to 4-line decoder or demultiplexer. So the same IC can be used either as a decoder or demultiplexer. But this IC contains two of such circuits, that is decoder or demultiplexer circuits. So you can use either one circuit or two circuits if required. Similarly, you have 74139 is also a dual 2 to 4 line encoder or 1 to 4 demultiplexer. So this also 74139 IC also contains two of such circuits. So it is up to the user that to use either one or two circuits out of the IC. So these two ICs belongs to the TTL family 74155 and 74139, and we have one more IC from the CMOS family. It is CD4555B. So this is a CMOS dual binary to 1-4 decoder or demultiplexer with outputs high on select. So this is also a dual IC, that means contains two similar circuits. They are 1 out of 4 decoder or 1 to 4 demultiplexer. So depending on the connection, the circuits can either be used as decoder or demultiplexer, and two of such similar circuits are present in the same IC CD4555B. So to see the working of the demultiplexers practically, you can apply the inputs and outputs and check and verify the truth table of the demultiplexer of the 1 to 4 demultiplexer by using these ICs in the laboratory. And we have some references. Before so to learn more about the demultiplexers, here the standard textbook references are provided, and also e-links are also provided from web, where you can see more material about the demultiplexers. So we'll summarize what we have learned in this class so far. So the outcomes of this lecture will be to define what is in my demultiplexer and to understand the working of a particular demultiplexer, 1 by 4 demultiplexer, and able to student should be able to write the truth table of the 1 to 4 demultiplexer and is able to draw the logic circuit using basic logic gates of the same, and mention certain important applications of the DMUX, and should be able to identify the TTL and CMOS demultiplexer ICs by IC numbers. So first we have seen the introduction of the topic, where we have seen that in large digital systems, if you want to transmit all the signals parallelly, it requires a lot of transmission channels, which is not economical, and in order to reduce the cost of the system, you will be transmitting all the signals onto a single transmission channel by using a multiplexer at the transmission end, and at the receiving end the information from the single transmission channel will be distributed over to or across a number of output channels, and this requires one more combinational circuit that is called as a demultiplexer. And as the name suggests, the function of the demultiplexer is exactly the reverse of the multiplexer. That is, it should collect the digital information from a single transmission channel, and it has to select one output channel, and it has to place the data corresponding to that channel on that, and next it has to switch over to the other channel, and it has to place the data corresponding to that channel, and so on. So the multiplexer and the demultiplexer circuits will make it possible to transmit um, different digital information, the digital information from a number of sources over a single transmission channel, and makes the large digital systems economical. And as we have learned about the multiplexer circuit in the previous lecture, so now we'll be looking at the demultiplexer circuits. So next we define what is a demultiplexer, a circuit which receives information through a single input line and transmits the same information over one of the possible 2 and output lines. And there we called have seen that the demultiplexer is also called as a data distributor, and after that we have seen one particular demultiplexer called 1 to 4 demultiplexer. There we have seen the symbolic representation of the 1 to 4 demultiplexer with data inputs and 4 data outputs, and to select one after the four data outputs we have seen, we required two selection inputs. And we explained uh, the working of the multiplexer by using a truth table. So we constructed a truth table where it has the selection inputs and outputs, and we have seen that the various bit combinations for the selection lines will select one particular output channel, and the data that is present on the input channel will be transmitted to the selected output channel. And after that, we have obtained uh, we have drawn the combinational logic circuit by using the basic logic gates. And to draw this, we had obtained the Boolean expressions for the outputs of the demultiplexer, and for D0, D1, D2 and D3. And after that, these Boolean equations expressions for the outputs are realized by using basic logic gates. And after that, we have applied, so this we have checked working of the 1 to 4 demultiplexer, for which we have drawn the logic circuit diagram. So this was explained by, for a particular bit combinations for the select lines S1 and S0, that is 0 and 1. So when we have selected 0 and 1 for the S1 and S0, we have seen that only the second NAND gate output is non-zero and it is equal to the data input, and the remaining outputs of the remaining AND gates, that is 1, 3, 4, are 0. So now the data input is connected to D1 output line, and whatever the input data will be transmitted to the D1 channel. And after that, we have seen the applications of the multiplexers in general, and we have also learned that a decoder with enable input can function as a demultiplexer. And finally, we have seen the important IC numbers of the demultiplexer ICs, both from the TTLI CMOS family. And finally, we have given certain references where we can get more information about the demultiplexer circuits. Thank you.